This is the first of several podcasts on modern atomic theory. Specifically, in this one, we will look at waves, energy, and the development of the Bohr atom. You see, the atom is a bit of a puzzle. It's composed of electrons and protons. They happen to be attracted to each other because the charges are opposite. In addition to that, electrically charged particles moved in a curved path are known to give off energy. But in spite of these facts, atoms don't collapse and they don't give off any energy. So how do we explain it? Well, we got to go sort of deep. J.J. Thomson won the Nobel Prize for describing the electron as a particle. He used the cathode ray tube in a classic experiment that you studied earlier in the year. Well, it turns out that his son George won the Nobel Prize in the 1920s for describing the electron as an energy wave and not as a particle. Confused? Oh yes. As late as the 1930s, physicists such as Sir Arthur Eddington in Britain he sounded like he didn't know what the heck he was talking about, and he freely admitted that he didn't quite understand it. Add to that, a Frenchman, Louis de Broglie, suggested that in fact, to understand the atom, you have to understand the behavior of electromagnetic waves, because he believed that the electron propagated through space as a wave. Well, you see, electromagnetic radiation propagates through space at the speed of light. And waves have a certain numbers of characteristics. They have wavelengths, they have amplitudes, and they have frequencies. As you can see from the graphic, frequency is the number of crests or troughs, ups or downs, that move past a certain point within a given time frame. The wavelength is how far apart those troughs or crests are, and the amplitude is how high or how low they are. Amplitude has very little to do with what we look at in chemistry, though. The equation tells us that the speed of light, c, is equal to the frequency, that's the v or nu, and lambda, which is the wavelength. Okay. Now the speed of light is a constant in a vacuum at 3.00 times 10 to the 8th meters per second. And we're going to measure the wavelength in meters and the frequency in units of hertz. And we will be doing some calculations with this. Electromagnetic radiation, in fact, goes from the very, very, very short wavelength, the gamma rays, all the way through to the very, very long wavelength, AM radio waves, something most of you probably no longer listen to. And sandwiched in the middle are the visible spectrum, and that is the part of the electromagnetic radiation spectrum that our eyes are especially tuned to receive. And it's how we see. The energy is directly proportional to the frequency. E is equal to h times nu. Energy is in units of joules. And so it's possible to determine the energy of a particular wavelength, and wavelength is related to color. Here we have a low wavelength, low frequency, long wavelength wave that's red. The intermediate is green, and the short is blue. The shorter the wavelength, the higher the energy, and blue is of higher energy than red, with green lying in the middle. Okay. Long wavelength, low frequency, low energy. High frequency, high energy is characterized by a short wavelength. And the calculations that are possible are this. The speed of light is nu times lambda. Energy is h times nu. And since lambda is related to nu by the speed of light, we come up with energy also equaling hc over lambda. Or, if we know the wavelength, we can get the energy. Likewise, if we know the energy, we can get the wavelength. And those are common rearrangements that will be on the problem sets. If you look at the visible spectrum, that is, take a prism, go out, you will see the full continuous spectrum of red, orange, yellow, blue, and green, and indigo, and violet, or Roy G. Biv. You may have had that mnemonic in middle school. However, if we use just a hydrogen lamp, we get 4 lines. And this is called a bright line spectrum, and listed down below there are the colors and the wavelengths in units of nanometers, 10 to the minus 9 meters, of the 4 lines of the hydrogen spectrum. Well, what do those have to do with anything? It turns out that Niels Bohr put together a model of the atom where he suggested that we had orbits about the nucleus, and that the electron would move inward from a higher energy state to a lower energy state, and he would give off light. And that light of a specific energy would be related to a specific wavelength. And that what you saw with the hydrogen spectrum was indeed the light given off by the electron moving between energy levels in an atom. And what Bohr did with this was propose that there were energy levels in an atom and that they contained all the electrons. This was a fascinating idea, and he came up with it because of an examination of those line spectra. Now, it's been partially disproved, but it is extremely useful to us still at this day. Bohr's model is the model that you probably came up with through elementary and middle school. We have a nucleus in the middle. That is containing the protons and the neutrons. The electrons are at the outside, and they are in orbits in Bohr's model. And there are many orbits, and those orbits also correspond to what are called energy levels. And the electrons are in constant motion. And that is the Bohr model of the atom. The electrons exist not so much in space, or are just out there, but they are out there at specific energy levels. And it is those energy levels that will be the focus of what we'll do in the weeks to come. So once again, Bohr's model was electrons can occupy only certain regions of space called orbits. Orbits close to the nucleus are more stable because they are at lower energy levels. Electrons can move from one orbit to another by absorbing or emitting energy, giving rise to those characteristic spectra. Now, his model couldn't explain spectra of atoms heavier than hydrogen, but we have extended it and we have used it, and it is still sort of the foundation of most of the energy level considerations that we use in chemistry today.